Well, welcome to today's presentation. This is a problem that can arise in your parallel coding of things, and so I want to make people aware of this problem and how you can begin to address it. There's different ways to address it in different things, and in many cases, this problem doesn't necessarily have to be worried about at all, because if you don't have much contention or you don't have any contention, then there's no real problem. But if you have a lot of contention, then there can be a problem. So without further ado, let's talk about false sharing and contentions in parallel code. So resource contention occurs when you need to access some shared resource, whether it's memory, a file, or whatever it is, involving multiple entities running concurrently or in parallel. So anytime you have something that's shared, a bunch of things need to access the same thing, that's contention. Now, if everyone's just reading and it's just one value, then there's no real issue, okay? But, that's a very small set of cases, even though it's fairly common. There are other cases when this is an issue. So that's what contention is. So now, if we restate this occurs, we want to think in terms of our programs instead of a general definition. This occurs when multiple processes or threads of execution attempt to use the same shared resource. So, like I said, if you have one value which exists and it exists before you need it, just sits there in that one value, and then everyone only reads it and no updates are happening to that value, happiness. Okay? No real issue, even though technically could argue there is a type of contention on reading that memory location, but modern hardware and everything else will cache things and all this stuff. It's not an issue. Okay? Why? Because you're reading the same value. You don't have to worry about reading the value that has been updated. That's where the problems start coming in with contention. When you have a value that's shared and you want to do an update, or you might do an update, it's just as bad, okay? You don't know when it's going to be updated and things like that, so there's no way for you to say, well, if I know when it's going to be updated, I could do things to maybe tell everyone you need to read a new value or whatever. There's a whole bunch of gotchas even with that, but we'll ignore that, okay? So when you have that problem, you got a problem, okay? And I'll discuss why. So modern computer hardware, all computer hardware pretty much these days, they all have, in your operating systems and programming languages, all have constructs to deal with resource contention. So whether you're using the hardware and you're programming really low level, or you're using a programming language, or even things in your operating system and all that, there's constructs there so you can deal with this problem. They're not put there because they're nice to have. No, they're put there because you actually need to use them if you're doing things concurrently. So in your programming languages, these are handled using mutexes, locks, semaphores, atomics, fences, barriers, whatever your programming languages or your libraries are using. If you've ever seen those things and wonder, hey, what are all those things about? If you're wondering what they're about dealing with resource contention. Okay? Now, if you do nothing about resource contention, outside the case where you're just reading the same value that never changes, if you do nothing about resource contention, that's not a solution. So if you're doing things in parallel, you, one way or another, need to deal with resource contention. So you either have resource contention or you don't. So if you don't have it, great. But if you have it, you need to deal with it. Otherwise, you're going to be computing incorrect answers because you're going to get incorrect values. They're not, all your updates are not necessarily going to be read properly. Okay? So the way you're thinking about your code isn't the way it's really running, necessarily. So let's deal with human beings instead of computer things. suppose you're in a room with 3 other persons. I don't care how many other persons. It's just that there's at least one other person. And every person has a pencil and eraser, and you can write and erase with. Okay? Awesome. However, there's a trick. This room only has one shared piece of paper. And for the sake of discussion, this shared piece of paper can only have one value written to it at a time. So there's one value on it. I don't know, let's keep it real simple, the number 7 or the number 5, a single digit or something. Okay? And the idea is if somebody wants to update the value on that piece of paper, okay, one has to first erase it and then write a new value. So there's only one value on the piece of paper. Now, there's no problem if everyone only needs to read what's on that shared piece of paper and it never changes, right? No problem, okay? And no problem if there's nobody writing to it and everyone wants to read it. But that's a big if, okay? But anytime somebody wants to update the value, even if it's to erase it and put the same value there, okay, you got a big problem. And that has to be dealt with. So when a person needs to update the value, the person, what do they have to do? They got to acquire that shared piece of paper. You got to get it because you got to erase it and that. So then you erase the value, you write your updated value, and then you put the paper back so everyone can read and write to it. So ideally, nobody can read and write to the paper while somebody is updating it. I say hopefully, but on a computer, don't hope. That's not a strategy. Okay? We can do much better. Now, similarly to this example, computer hardware, operating systems, programming languages, and all this, there's this problem. Any shared resource has the same problem. It's like that shared piece of paper, and you want to read and write a value to it. Okay? Now, you of course have multiple memory locations and multiple shared resources, so you can have multiple shared pieces of paper. That's fine. You can generalize in that way. Okay? So, if everyone's just reading it and the value is there to begin with, no problem. No updates to it, no problem. Okay. But, of course, we often want to update things. So, we're going to have an issue when we want to do updates, and that's updating the shared piece of paper. Okay. Now, there's a kind of shared resource contention hidden from programmers. I put hidden in quotes here because once you know about it, it's no longer hidden in a sense. But I say hidden because you have to recognize it in your code. If you see it manifested at all in your code, you'll just notice your code's running slow. Okay? Things will otherwise appear to work fine. This is a specific kind of resource contention, and it's called false sharing. So, very similarly to the notion, the scenario I presented just a moment ago, now imagine you're in a room, could be the same room, whatever, with 3 other persons. And again, I don't care how many other persons there are, there's just more than one. So you have some level of concurrent or parallel behavior here. So every person, including yourself, has a pencil and eraser still. And there's one shared piece of paper in this room which you all use in the same sort of way. Okay, but this time we'll have the shared piece of paper and we can have exactly 4 values on it. And each of those 4 values, one is for person 1, another's for person 2, person 3, another for person 3, another for person 4, and you only read and write your own value. You don't care what anyone else's values are. But here's your problem. There's one shared piece of paper, and if anybody wants to update their value, they don't care about the other's value, they don't touch it. But if they want to update their value, they got to get that shared piece of paper, erase it, update their value, and put it back. Okay? And the problem is, when they do that, no other person could read and update their value. Why? Because they're modifying the sheet of paper. You can't see the paper, they're busy messing around with it, and until they put it back where everyone can see it, you can't do anything. So what you're doing is you're waiting. The computer term for this is called being stalled. If you're talking about instructions, you're using tools like perf or whatever, and you're looking at, is my computer just busy waiting for something to happen instead of doing stuff? Well, that's an instruction stall. Okay, and you will wait in your computer. If you need to get something from memory and it's not in any of the caches or anything like that, your computer will wait for that to come before that, for processing to continue. Why? Because it's stuck waiting for that before it can do the next step. Okay, so that's a bad thing. That limits your concurrency. So that is what false sharing is. So false sharing is a type of contention that's occurring because things are located close to one another. So even that sheet of paper, very importantly, every person had their own value. They didn't care what the other values were. They totally didn't care. They don't care. They're not touching them. They're not reading them. They're not doing anything. But because they're on the same sheet of paper, anybody updating their value affects everyone else. Okay? That's called false sharing because you're sharing that piece of paper, but you don't know it. So in a sense, it's sharing, but it's false because you're not really sharing. The program is just saying, I need to update this value in I, and you want to update I. Well, if it's next to another value, another part of the program is updating, you've got a problem. Because if they're on the same shared piece of paper, you got a problem. So how do we deal with false sharing? Okay. Well, you have to recognize when you have multiple values close enough to one another in memory. So this happens often. How many of you have put int I, comma j? Boom, I and j are right next to each other in memory. Or double and two double variables next to one another, or you have an array of variables. Obviously, array elements are right next to each other in memory. So it's not hard to see how you can have things next to each other in memory. And this can happen in any programming language, not just C, C++, or Fortran, but it can happen in any language. Okay, so when values are close enough, and I'll talk about a little bit later what close enough means. But if they're close enough, you're on the same sheet of paper, conceptually. Okay? Now, how do you solve it? You recognize situations when you need to access things frequently. I don't know, update your values frequently. And you recognize them and you say, oh, okay, I'm doing this commonly with values that are close enough to one another, but those values are being updated from separate threads of execution. Okay, or processes if you're using processes. So how do you fix it? You basically locate them further apart from one another in memory. Why? So they're not on the same sheet of paper. So the paper analogy I'm using here stands for something in the computer. And you'll say, really? Yes, this is how you do it. Okay. So how do you know if you're on the same sheet of paper? Well, the easiest way to understand this, the answer is, oh, you don't want to be on the same cache line. And people say, what the bleep is a cache line? Okay. Your computer, when you get your computer or any computer you have, you probably know whether your computer is 32-bit or 64-bit or any number of bits. When you look at a computer and you buy a computer, like they like to advertise 64-bit or 32-bit or whatever. These days, all computers are 64-bit, but there's different numbers of bits. Now, that go with this, and you'll say, what is that? Well, when a vendor says, hey, our chips are 64-bit or 32-bit, what does that mean? It means that the computer will read and write data in chunks of that amount. Okay? So when I say read or write data, it's really reading and writing to and from memory. So a 64-bit computer will typically read and write data in 64-bit chunks. That's 8 bytes. Okay? 32-bit computer will do 32 bits or 4 bytes at a time. So in other words, you'll say, wait a minute. So if I have a 64-bit computer, that's 8 bytes, and I want to update 1 byte of memory, Okay, fine. But you're saying here, if that's the sheet of paper, the 8 bytes, and the second byte, the byte that's right next to it, the second byte in that chunk, if another thread updates that byte, then that's the same sheet of paper and the other thread has to wait? Exactly. The other thread has to wait. Now, the reason this slide says typically we'll have a cache line size of 64 bits. A number of you might be familiar with Intel and SIMD instructions, or they say it does so many things at the same time. Intel CPUs, for example, will often do it with twice that width. Instead of 64 bits, it'll be 128 bits, so 16 bytes. This is designed by the hardware vendor. So whatever it is they do, it's hard-coded in the hardware. You can't change it, okay? But in general, if a computer is a 64-bit computer, it'll read and write these chunks 64 bits at a time, okay? It does not read and write a bit or a byte at a time. It reads and writes these little chunks at a time, and these chunks are called cache lines, okay? The smallest unit of whatever it will do. Now, if your computer has L1, L2, L3 caches, typically they do, they're larger than 64 bytes. Does this false sharing problem matter in practice? The answer is no, not in practice, because, well, the cache stuff and how they handle, and I don't want to get into it, statistically speaking, it won't matter. Okay, there are some cases where you can run into issues, and if you're totally maximizing performance, you might want to deal with things, but it'll be very hardware specific. How hardware specific? How the caches behave on the hardware you're using. So in practice, though, it doesn't matter. Don't have to worry about them. It's not going to be significant in your code, okay, outside of some maybe niche, very niche cases. So now, if we got to locate things farther apart, some of you are thinking, oh, does this mean I need to space things out with variables? And what do I do about my array? And what do I do about things like this? Okay, so there's straightforward ways of dealing with this. With the 2011 C and C++ standards, the standards committees brought in this notion of a line as. Now, I'm going to talk about C++, but C also has an align as operator in it, and it does the same thing as in C++. Spelling's a little different. It starts with an underscore, okay? But it does exactly the same thing. So you can do that in C and C++. Other languages, if they don't have the equivalent of a line as, which I'll do an example shortly, in the language, then you have to space things out manually. Do one way or another, space them out, and a clever trick to space things out is just dynamically allocate it at the beginning of the program or something like that. And dynamically allocated memory gets put somewhere else in memory, and typically the spacing that separates dynamic memory allocations are far enough apart that your false sharing issue will no longer be an issue. Now, in C++, the C++ 11 standard brought in hardware destructive interference size and hardware constructive interference size. So that deserves a mention. Those values are important for this problem. If you're unsure, just use the larger of the two, which would be hardware constructive interference size. If you really got to conserve memory, but you still want to deal with it, then use the destructive one. Now, typically, on all computers I can think of, the destructive size is 64 bytes, because all modern hardware I can think of right now, including ARM and this and that that's out there, the cache line size is 64 bytes, typically. So if it's a 64-bit computer, the cache line size, it's 64 bytes. That's what these systems are typically using, okay? So draw a connection to that. So if you are dealing with a 64-bit computer, okay, your cache line will at least be 64 bits, which is 8 bytes. But typically on modern hardware, they actually, the cache line size will be larger. So it'll read and write the smallest chunk like that, and it'll be your 8-byte integer or 4-byte integer and all that. Yeah, the hardware can do that. But typically, you want more performance. You want fast speeds. You want high speeds for your memory transfers and all this stuff, because people want faster computers. So computers actually read and write larger chunks, and modern machines, that is a 64-byte chunk. Okay, so the sizes that you want to use will be 64 or larger, but at least 64. Okay, so you use align as to space things further apart. So let me show examples, and the examples should be here. And if I go to the other window, here we go. Okay. Now, first of all, let me show you the problem of false sharing before we talk about code. So if I take false sharing and I put everything 1,024 bytes apart. Okay, so if I have memory and the values I'm reading and writing, and each thread gets its own value. Okay, and I put them 1,024 bytes apart. And just to be paranoid here, I'm just going to rebuild this since I had to transfer things to a different computer. That executable might not work. So this is just generating code with different spacings and compiling them. Okay, so now if I go 1,024 bytes apart and I run this, okay, what do we have here? Well, you can see my data alignment size is 1,024 bytes. Okay, my interference value is 64 bytes. And if you don't know what it is, or you're using another programming language, or you're having weird compilation issues, you can just hard code 64 and probably be okay. If you're totally paranoid, double that to 128 on Intel chips. You might want to do that, and then you'll be okay. Space things 128 bytes apart on your Intel CPUs, and you'll be fine. Okay, so now if I have one thread, okay, updating my value, and I forget how many times I did it, let's say 10 million values or whatever, I forget how many times I did it. Great, I did it in 0.05 seconds. Fabulous. Okay, so if I do two threads, each updating their own values, this is separate sheets of paper here. Look, my time, 0.05 seconds. Okay, same thing, 3 threads and all this. The second value is important here because I had to take this value, divide by the number of threads, and you can see the values I get are more or less the same. I do get a performance loss due to memory issues, normal. The further apart things are in memory, the more the hardware has to do stuff to deal with loading memory and all this stuff. So it slows down a little bit as I go further and further away. But this is good. That's good speed. We'll say, what happens when they're all on one sheet of paper? So if I have multiple threads, so I'm going from 1 to 16 threads here on this computer, okay, and this will happen on any computer where you have multiple threads running. Okay, the exact timings will vary, but the same kind of problem will happen. Watch what happens. So all of these values are more or less 0.05, or it goes up to 0.08, but it's very quick. Watch how slow this is just by being all in the same cache line. Notice 0.05, the second one with 2 threads is 0.2, with 3 threads it's 0.3, with 4 threads it's 0.4, and you keep going up, and it's just getting worse and worse and worse. You can see the other one finished right away. Right here, like 15 threads took 2 seconds. 16 threads took 2.2 seconds each to do the same thing. So up here, spaced further apart, 16 threads took 0.0, I'll round it, 0.09 seconds to run total. To do the same exact thing as down here, 16 threads each took 2.2 seconds. to run, to do the same exact thing. No difference. Okay? The only difference between these two programs is my data alignment here is 1. In other words, everything's immediately next to one another. And so these 16 threads, they're accessing 1 byte of memory. So they're all on one cache line, and they're all running, interfering with each other for this. And why is this? Well, just like in real life, if we share a same piece of paper, and if I update that sheet of paper or you update it, any one of us updates it, okay, I can't look at it while you update it. And if I do, I'm just going to see the old value. That's what happens. I'll just see the old value, but it's more complicated than that. But when you're done with it, you put it back. Now, what we do as people, when somebody puts that sheet of paper back, we look and we say, oh, the paper's back, I can read it again. On a computer, that doesn't happen. On a computer, when the value is updated, the hardware in your computer has to tell the CPUs, the other CPUs trying to do stuff with that memory address, it has to tell them that that memory address has been updated. And it has to transmit the update to the cache system. That's called bus traffic, BUS, bus traffic, right? And your computer gets busier and busier transmitting all of these updates to all the other CPUs in the system, okay? And that's what slows it down. Because you look at the code and you say, what's the difference? There is no difference. It's where, the only difference is where you're locating your values in memory, okay? So if we were to quickly look at this program, let's just look at parts of it, okay? So each thread just counts down, I think this is 10 million, whatever, how many zeros do I got here? Yeah, that's 10 million. So each thread is just counting down from 10 million. So if I come down here and just point out to you that I have a for loop right here. And all I'm doing is counting down from 10 million to 0. And every time I do that, I'll add 1 to my byte of memory. That's what that line does. Now, some of you will say, well, when you add a byte of memory, wouldn't you just go like plus plus or that in the variable name? And the answer would be yes, you would. But if you write it that way in your code and you want to demonstrate false sharing, you won't see it. Because the processor will say, oh, we're updating that value, and if the processor figures no other processor needs to know about it, it will just keep the value in a register. And if it keeps it in a register on that CPU, it will update the register really fast, and it will do that in a for loop really fast because it'll say, I don't need to do anything else. And when it's done with everything, it'll write it back to memory. Okay? So in other words, you won't see any false sharing because each CPU just does it on its own. It doesn't look for an update. So I need to tell it to look for an update. Now, recall what I said. Mutexes, semaphores, locks, atomics, barriers, and fences, those terms, so-called synchronization, if you're a Java programmer, the keyword synchronized or volatile in Java. In C++ and C, don't use volatile. That doesn't do what you want. You want to use atomics. Okay? All those things allow you to deal with those problems. And those are issues on their own. Okay? So this program I have here, and this is why I don't have slides on it, because I don't want to get into too much of the weeds of things because every program is different. But in this program, in order to make the updates to my variable visible to all other things running, I used in this program an atomic. I could have also used a mutex and a lock or whatever. But in this one, I used an atomic. Okay? Why did I do that? Because I could do it the fastest way possible. Okay? But this is the only way you can say to your program, these things are the only way you can say to your program, hey, I'm updating this value. Why? Other things need to see it. So advice number 1, if you have something that doesn't need to be shared with other threads, declare that variable, that something, whatever it is, use it in that one thread only. Make your life simpler. Don't even share it. If you make it a shared resource, you will marginally slow your computer down. How bad is this? Well, once I was dealing with an issue, but it's very easy to have. I had a global variable or some variable in main, and I was saying, oh, I'll pass it as an address to the thread I need to do it with. And that's fine. You can pass it as an address, except the compiler will say something else might modify that variable. So I need to be really, 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 really conservative, and I will generate the code in a certain way. So instead of running at the maximum possible speed, the compiler will be ever so slightly slower because it has to make this assumption. Compilers are pretty stupid, okay? So, and that's by design. That's how they do things. So what you'll find is that code's slightly slower. Now, if you only take a second to run it, who cares? But if this is your part of your computation that takes hours or days to run, the time will be significant. So let's say it takes 6 days to run total. Don't be surprised if you just lost several hours of compute time because you had that variable in main that you just passed by reference to a thread and only one thread uses it. Don't do that. Ideally, just have it in that thread. So the compiler completely knows it's not elsewhere and doesn't make assumptions about aliasing and other things that have a performance impact on your code. Now that's kind of in the weeds, so I'm not going to show that as an example, but that's something to be aware of. Now, here's the issue. If all you do is declare your variable, so don't even worry, I have char data, like if you put here, if you want to declare your variable, like char, or many of you might say double, and D or X or whatever, like if you want X, great. You want a variable like that and you do it, hardware by default will automatically align your variable to what it needs in memory, okay? And if you put another variable after it, okay, unless it's more than that sheet of paper in size, so unless it has to be bigger than 64 bytes on its own, they're on the same sheet of paper, or can be, okay? Because they're immediately side by side. So if you want these two double variables to be further apart, okay, and you can use that variable I mentioned that's in the standard library, but if you don't have that available, or you don't know what it is and you just want to make things work and you want things to be 128 bytes apart, just do this. Align as. You can't specify it less than what the hardware allows. If you do that, the compiler will give you an error. So just put align as, and if you put 128, then that tells the compiler that this variable X has to be aligned to the start of a 128 byte chunk. So in other words, the starting address has to be divisible by 128, evenly divisible. Okay, so every 128 bytes, this split. This means that if I did the address of X and the address of Y in my code, and I subtracted them, I'm going to get 128 because they're immediately next to one another. If you need something spaced before a variable, you have to just declare something that's big enough. Align as only works for that variable and what follows it. Okay, so the compiler will add padding for you. So that's all I did here. So when my code compiles multiple times and specifies the macro custom align, which is whatever value I want to separate things with, could be 128 or whatever, okay? This align as before what follows it allows my variable to exist, and then it puts data after it. The old way, before C++11 and C11, how would you do this? You would have your variable. So here, let's say your variable is a double. And if you had double X and double Y and you wanted them to be further apart, the old way to handle this would be to declare a useless variable. I'll just call it unused. And you put as many bytes as you would need to have them separated, taking into account the size of the variable. So let's say we want 128 minus however big a double is. Okay, that's what you would do. And the compiler would complain that unused is an unused variable. but that's what you would have to put the spaces in it. So nicely now with C++ 11, you no longer have to do that. You can get rid of that kind of code. Just put a line as 128, and you'll get the padding added after it to that effect. Okay? Nicely as well, you can use a line as in your structures. So if you know you have a struct or a class in your code, and you need to space things apart because they are indeed used by separate threads for whatever reason, then you can put a line as in front, put the alignment you need them to be aligned to avoid false sharing, which on Intel chips, if you're doing anything on modern clusters and that, set it to at least 128, okay? And you will avoid false sharing as a problem. I should say at least 64, but you probably want 128 on Intel systems, and then you're good. Now, what's really cool about that in this program is you can see the benefits. I have this struct datum here, okay, and the benefit is down here. Look at this. I have my vector, so I have an object to declare my global array, okay, and I'm going to have so many copies of these. Who cares, okay? All I have to do is put the name of my type, and the compiler knows it has to align the stuff that's inside my type. So that's great. So if you have to, normally you might say, I have a vector of char. Can I put a line as with char in the vector? No, you don't do that. Just throw it in some sort of struct, and inside that struct, put your char, or your double, or your complex numbers, or whatever you're doing, and then just put a line as in front. And then it will get spaced out properly by the compiler, and you'll be happy. And what is the benefit? Well, the benefit is like what you saw, quit out of here, what you saw earlier when I said, hey, let's put these further apart. Now, I did 1K before, but we can do 128 bytes apart, and we can see that we're getting the same performance as when it was 1K apart. But if we are only 2 bytes apart, there's overlap, and we get this false sharing behavior because they're, in this case, they're still on the same sheet of paper. Okay, why? Because my sheet of paper, okay, is effectively 64 bytes. Okay, and I only have 16 threads of execution here. So if I'm only using 1 byte each one, and I just put them 2 bytes apart, they're all on the same sheet of paper, and I get this slow performance. So that's what you want to avoid, because there's nothing wrong in the code, and this problem happens more often than you notice. And this is another reason why you benchmark your code, because you can see, why is this piece of code running slow? And sometimes it's because 2 things are close to one another, too close to one another in memory. You just need to put them a little further apart, and then the magic of modern caches and all that, you can be happy. And the overheads of other issues, such as things on the same L1 cache and all this stuff, are largely non-issues. They can be, but usually they're non-issues. If you do have issues that you're worried about, then try to have each thread processing data that it's in its own chunk of memory, and doesn't touch anything else. That's usually the better scenario to deal with things more easily. Anyways, I'll wrap up with this. If you have any questions, by all means, please ask. And be aware that when you write your code, if you have things right next to one another in memory, and you're always updating them and reading from them at the same time, but even just doing only updates, the computer is designed to assume, hey, people might read it. You want to know that the updated values can be seen by other threads, and that's a really important point. You have to do things to make sure they're seen by other threads in modern code. So just be aware when things are located close to one another, there can be problems with this. Even though you'll say, my code, hey, thread 1 accesses this byte, and thread 2 accesses that byte, and they're not the same bytes. But if they're on the same cache line, you got a problem. I'll end with this. And thank you for coming.